Now I would like to invite Mr. Nanocomposites to present his paper titled On the Determination of Characteristic Fracture Toughness Quantities of Micro and Nanocomposites.
So thank you for the nice introduction. I'm working on the determination of the intrinsic fracture toughness of materials in micro and nanocomposites. And I'm Darren Kozitz, and I'm from the Materials Center in Rome. First of all, I would like to thank my co-workers, especially my mentor, Otmar Kolednik, for the collaboration. For the motivation, I would like to show you this picture of a foldable microelectronic device. This is a rollable screen shown by LG Electronics at a tech conference in 2016, and those devices will be on market very soon. And the problems in such devices are that a very high number of materials is used in those devices, and those materials have to have a lot of functions, so the design is very complex and the loading conditions are also very complex. So the thing is that the failure behavior in such devices is not trivial, and we have to find out the critical loading conditions in such devices because the reliable performance is essential. So what the main goal is the determination of the fracture toughness of single materials and the critical loading conditions in thin film stacks. And what we looked at is this example, and I will use this example in the presentation. It's a copper tungsten 3-layer system deposited by physical vapor deposition on a silicon substrate. And what the issues are in such a systems is that the material inhomogeneities influence the crack tip conditions, and experiments only are not sufficient to determine the fracture toughness of single materials. So before I come to that, we have to take a step back and ask ourselves what the condition is for crack propagation in a material. We know that every material has a fracture toughness, and if this material is loaded, the crack tip experiences a crack driving force, J tip. And if this J tip is equal or larger than this critical fracture toughness, JC, this crack will propagate. And a very convenient way to calculate the crack driving force in a material, as my mentor was talking about it earlier today, is the configurational force concept. And in a homogeneous material like this, which has only a crack, the crack driving force is determined by the external load which is applied on the material, which results in the driving force J far. So in a homogeneous body, this is simple. And if we go to inhomogeneous materials or bodies, such a body can have, for example, an interface between two materials, and there is a jump of material properties at the interface. So we have interface configurational forces which induce an additional term which is called the interface term. Additionally, we can have a gradient of material properties in a layer, here for example in the layer L1, and this gradient causes gradient or bulk configurational forces F gradient, and those configurational forces induce a gradient term C grad. So in an inhomogeneous body, J tip is not equal to J far anymore. we have to add another term, which is the C inhomogeneity term. And this C inhomogeneity term in this case is a sum of the interface term and the gradient term. And we are talking about the shielding effect on the crack tip if this C inhomogeneity term is smaller than 0, and we are talking about this anti-shielding effect if this inhomogeneity term is greater than 0. So what do we have to do to determine the fracture toughness, the intrinsic fracture toughness of every material in this composite? Is we built an elastic plastic model of a microcantilever bending beam, and we loaded it with a constant load V. And what we need as input for this model are the residual stresses in the system, the material behavior, and the critical loading conditions in this stack, of course. So what we did in earlier work is that we calculated the residual stresses with the so-called ion beam layer removal method, and we have calculated the flow behavior of the materials of tungsten and copper from nano-indentation experiments. And what we can say is that the residual stresses and material property jumps at the interfaces will contribute to the interface term, and the residual stress gradients inside the layers will contribute to the gradient term. So by also having the initial crack length and the critical load from the experiment, we can calculate, for example, in this case, the initial crack is inside the top tungsten layer, and we can calculate the critical J integral value for the tungsten layer. And if we consider the complete conditions, which means that the flow behavior for the two materials is considered, and also the residual stress distribution is considered. So in this case, the C homogeneity term is a total of this interface term and the gradient term. We have determined a value of 21.2 joule per square meter for the critical J value. But if you neglect the residual stress gradient inside the layers, we calculate a value of 25.2 joule per square meter. And just to show you the difference to if we consider a homogeneous linear elastic cantilever material, we would get the JC value of 2.8 joule per square meter. So this is very far off. And what is important is that this value compared to this value is 90% higher. So it is very clear that this gradient term has to be considered in the calculations. And this is shown here when we look at the critical loading conditions for an arbitrary load of 1.5 micrometers in bending for different crack lengths coming from the surface. If we look at the critical J values, which I have told you before, is that the critical J value, which doesn't count in the gradient term, overestimates the critical conditions in the tungsten. So this value shows you the truth in this case. And what we can also say is that the copper interlayer is creating an arresting environment for the crack. So after the crack propagates through the tungsten layer and it enters the copper layer and the crack gets longer, the crack driving force decreases, and this means that the crack is arrested inside the copper layer. So in summary, the intrinsic fracture toughness of materials in thin film stacks depends on the residual stress variations at the interfaces and inside the layers, and the material variations at the interfaces. And And you could also have material variations, of course, inside the layers. And the interplay of those effects can be utilized to optimize the design of microelectronic components. So, thank you for your attention.
Thank you, Mr. Kozis, for your